Good e- Right. Good evening, my distinguished guest, SEDS President, division members, and friends. I am Rehan Amarasiri, second year undergraduate at Sri Lanka Technological Campus and also PR manager of SEDS SLTC Satellite and IT Division. Today, we've all met here for an experience and knowledge exchange webinar on design and development of a satellite ground station, hosted by SEDS SLTC Satellite and IT Division. Let me make a few important announcements before we commence the webinar. We kindly request our audience gathered here today to mute your microphones to avoid any disruptions due to background noises. A Q&A session will be held at the end of our webinar to clear up any confusion. Please complete the feedback form provided at the end of the webinar. Okay, to begin, let me provide a brief overview of SEDS. SEDS stand for Students for the Exploration and Development of Space and is a non-profit international student organization that empowers young people to participate and make an impact in space exploration. SEDS helps students develop their technical and leadership skills by providing opportunities to manage and participate in international projects as well as to attend conferences, publish their work, and develop their professional network in order to help students become more effective in their present and future career in industry, academy, government, and education. The Satellite and IT Division of SEDS SLTC have organized SatNet 22 as a webinar on the design and development of a satellite ground station. The ORAGAN 2 satellite is being developed in Sri Lanka this year by SEDS Sri Lanka, which is going to orbit in India, and its ground station will be built at our university. This webinar will assist in laying the foundation for the ground station design that is to take place on our campus. For this session, our main guest speakers will be Mr. 𝑤𝑒'𝑟𝑒 𝒂𝒐𝒖𝒏𝒈, Electrical Engineer, Ground Station Manager at the 𝑟𝑒 Clarke Institute of Modern Technology, Sri Lanka, and Mr. 𝑡harindu 𝑑ayaratne, Electrical Engineer at the 𝑟𝑒 Clarke Institute of Modern Technology, Sri Lanka. We hope that this session will give an participant an opportunity to widen their knowledge of ground station satellites. Okay, let me now give you a quick overview of our special guests. Mr. 𝑤𝑒'𝑟𝑒 𝒂𝒐𝒖𝒏𝒈 is an electronic engineer at the 𝑟𝑒 Clarke Institute for Modern Technologies in Sri Lanka and former Lankabell Assistant Engineer. He also serves as the ground station manager at the 𝑟𝑒 Clarke Institute for Modern Technologies and is a member of the Nano Satellite team. He also worked on 𝑟𝑎𝑣𝑛 Nano Satellite development team. Mr. 𝑡harindu 𝒂𝒑𝒻, an electronic engineer at the 𝑟𝑒 Clarke Institute for Modern Technologies in Sri Lanka, is our second guest speaker. Mr. 𝒬𝒑 is a space engineer at Japan's Kyushu Institute of Technology and the designer of Sri Lanka's first nano satellite, the Ravana 1. I would like to invite Mr. 𝑤𝑒'𝑟𝑒 𝒂𝒐𝒖𝒏𝒈 to share his knowledge and experience on design and development of a satellite ground station. Mr. 𝒬𝒑.
Yeah, audible, my voice?
Yes, sir.
Okay. Could I share my presentation? Okay. Okay. Is it seeing you?
Yes, sir.
Yes, sir.
Okay. Okay. Good afternoon, everybody. I'm 𝑤𝑒'𝑟𝑒 𝒂𝒐𝒖𝒏𝒈. This is the presentation about the designing and development of nano satellite ground station. And at the end, Mr. 𝒬𝒑 also here. the presentation totally held by me, and the Mr. Tarun Jayaratna joined the Q&A session also. And first of all, we what we going to introduction of the ground station, and this is the introduction of the ground station terminal, and low Earth orbit satellite communication systems. This is my content of my presentation, and technical specification of the ground station operation, and our achievements. Actually, introduction of the ground station, when we consider about what is the ground station terminal? Is a ground station terminal is a generally we know the ground station terminals are there's some it may be some aircraft ground station we call ATC, Air Traffic Controller Center. It's a one of the ground station, or satellite ground station, or any ground station that communicate with the space segment. In this slide, we express there are some ground station and satellite and communicate with each other. The space segment there and ground segment. Okay. Then this is the example for the some ground station. We know the Voyager outside of the solar system. There's some special ground station in our Earth, and Cassini. Also, there's some ground station also around the world, orbit around the Saturn. It's Cassini, and geostationary satellite. We know the geostationary satellite approximately 35,000 kilometers above the Earth sphere, and we call it's called Clark's orbit also. And then a special thing today, our focus thing is the low Earth orbit satellite. That low Earth orbit satellite we generally called around 400 kilometers surrounding, but some satellites they put into the 300 kilometers something above the 400 kilometers. That's mean 600 and 800 kilometers. But generally we call low Earth orbit satellites around the 400 kilometers. Then the ground station, as I said earlier, aircraft. Aircraft, there's some ground station called ATC. Actually, ATC, Air Traffic Controller, they communicate with this aircraft, and they control the aircraft heights and other things. And actually, it's also some ground station. Then this is some picture about the 70 meter wide radio antenna, especially we call deep space networks communication. That means very far away space objects we can communicate. We have to communicate. In that situation, we have to build very big antenna, because the antenna, when antenna reflector, actually this part is called a reflector. This reflector, when you see big reflectors, the antenna gain is high. So in that situation, there's some another phenomena also. Then beam width also very thin, and the transmission shooting area very high. The other one is 35 meter diameter dish antenna. It's also used for the I think control the Cassini air system, Cassini system, and those are establishing someone in Australia, near to Australia, and others are both are in Australia. In most of the cases, that type of big ground stations antennas used for the most probably space communication. And this is another example. The most left side image, there's some dish antenna. Sometimes it may be 3.5 to 18 meter range reflector. Most probably used for geostationary satellite. That reflector types, depending on some frequencies, there are some bands, S band, C band, KU band, some bands there. So according to that band, our utilized bandwidth also change, and then antenna properties also change. Actually, this type of dish antenna used for the geostationary satellites. And most right side image, you can see VHF and UHF antenna system. Most probably we use LEO satellite operations, VHF and UHF. Actually, if you can see, there's some cross boom and antenna main boom. The antenna main boom, there's some directors also. I think this image not clear the antenna directors, but if you see them carefully, we can see the antenna directors also there. This is the VHF and UHF antenna. Actually, in a LEO satellites, we have to consider this type of antenna. So this is the what we call the okay. This is some actually LEO satellite system. There's a ground station and satellite there, and we called in LEO satellites 400 kilometers above. This satellite speed nearly 7.6 kilometer per second. 7.6 kilometer per second. This is the speed. It's a very huge one. Very huge, because that speed is totally depending on the height of the satellite. If you think above the 400 kilometers, that value goes down. It may be a 6 point something or 5 point something. And below the 400 kilometer, that's been around 300 kilometers, it's that number goes high. That means it may be a 8 point something. So that's the reason that speed depending on the height of the satellite. In a special case, we have to know the window of the communication. That means in 400 kilometers above satellites, that means LEO satellites, in horizon to horizon transfer, horizon to horizon, there's a horizontal level, horizon to horizon transfer, approximately 11 minutes. We call nadir pass. Nadir pass means it's 90-degree overhead pass, called nadir pass. That type of pass approximately 11 meters. So in that window, actually the 9 minutes is the, I think 9 minutes, around 9 minutes is the very best time window. So in that time, we have to send some command to satellite and receive some data from the satellite, and our total business with the satellite, we have to do within this time window. Okay. This is the some properties of the ground station. First thing is the capability of the uplink and downlink. Uplink means transmission from the Earth to satellite. Downlink means transmission to satellite to Earth. Okay, capability of the uplink and downlink. That means we have to use a transceiver and antenna system, and there's some specific another apparatus I'll explain later. Those are the main parts. Then high gain antenna, especially mention the high gain antenna, but this is actually depending on the link budget of the satellite and this system. That high gain antenna, if we use high gain antenna in LEO satellite communication, we have another advantages also, because when antenna's gain is high, the beam width also very thin. In that situation, we can track the satellites in very small elevation angles. If we use a low gain antenna, the beam width it's comparatively something big, so that beam width in that situation, the signal path can be interact with the Earth. We call it bulge. We call Earth bulge. Then the precise tracking capability. In LEO satellites operation, we have to move the antenna. We have to rotate the antenna towards the satellites. So in that situation, we have to use antenna tracking system. So that antenna tracking system should be precise. And another thing, Doppler correction. We know in moving items, normally in our environmental example is in ambulance. We know sometimes we have some. I think we all have that experience. Ambulance, there's some horn there. When operate the horn towards the other side, there's some we feel the sound is very high, then normal, then low. This is the phenomenon of the Doppler. The same thing apply in this situation. This is also frequency. This is radio frequency. The ambulance there has a sound frequency. Also, same phenomenon. In overhead the satellite, when we situated the satellite in our overhead, the frequency there's some nulling. I will explain that one. And then structural stability of the antenna tower. It should be the perfect one. Otherwise, antenna tracking, that means satellite tracking system, have some big problem, because there's some another moving object antenna. Same time, the structure has some instability, so there's some big problem. Okay, So we have to consider about the structure of the stability of the antenna tower. Then this is the Doppler system. There's a Doppler correction plot. There's some blue line and red line. That blue line represent the Doppler rate. That's mean rate of change of Doppler in hertz per second. And a red line, this is the normal frequency. We know the operating frequency 437.375. That frequency, how to receive to our ground station. That decimal numbers, pointing numbers, it may be varied. 3.375, it may be varied. Okay, due to Doppler effect. So we have to correct that. We have to correct to receive to perfect signal. That part done by the satellite tracking softwares. Normally we use famous one Orbiton, and another one SatPC32 also there, and gPredict also. But I'll explain. SatPC32 is the we use one, and Orbiton also we use, but for some prediction requirements we used for that Orbiton. Otherwise, we use SatPC32. Okay, then this is the basic block diagram of the ground station. You know, there's some transceiver, antenna, rotor control system, and satellite. I explain now uplink and downlink thing, and main part there, PC, personal computer there, and transceiver, antenna, rotor. So because we have to track the satellite, we have to track the satellite. We have to use track the satellite. So this is the some we get this as an example. Ravana 1 ground station the properties. Actually, uplink frequency there 437 approximately, and downlink 435 point something, and antenna gain 13 dBi. This is the ACCINT we used antenna. Our antenna has a 𝑚ASPRO is the production 𝑚ASPRO 13 dBi cross-polarized 𝑦𝑎𝑔𝑖 antenna. Okay, 𝑦𝑎𝑔𝑖 antenna. Actually, we have VHF and UHF antenna. In this case we use UHF one. It's a very old one. I think it's purchased to ACCINT 1988 or something. But we established our ground station 2018, begin the 2018, and our satellite launch the 2019. 2018, I think November or December, we started the established ground station. In that situation, antenna, there's no any directors, only dipole is the working. Other any other rest of parts all are got damaged. So that we replace all the things and we refurbish that. So, and another thing is transmit power. It is 50 watt. We used ICOM 9100, the transceiver. It's a 50 watt transceiver, and we use a modulation GMSK. That GMSK modulation done by in TNC part. TNC I'll explain. And data rate for 4,800 bps. Tracking in our system, auto and manual there. In tracking system, we use auto system, and receiver sensitivity. It should be more than minus 135 dBm. I think in our ICOM 9100, it's nearly 140 dBm. And this is the complete block diagram of the ground station. In our ground station, there's some dark blue part there. Dark blue part mean this is the outdoor parts. UHF antenna, and that antenna connect with the rotor motor side. That's mean outside part. Actually, 𝑔𝗲𝒂 𝒂𝒂 we used one, but after few months we replaced it in Kenpro one. Then normal ground station, we established the LNA. We put the LNA, but in our case, we don't want to LNA, so we remove that one. And directly antenna connected to the radio via arresters, lighting arresters. And radio is ICOM IC 9100, and rotor controller also inside the ground station. Then there's some special case. Rotor controller is a very this equipment is very old one. Actually, this equipment used for most probably use the amateur radio operators. They use that equipment, and they used in manual mode. Most probably manual. Auto mode also they use, but most probably they used in manual mode. But in our case, we have to use auto mode. That means we have to control it through the PC. So that we have to use some interface to compatibility with the PC. So use the port interface GS232B. I'll show you that that images also. Then other side TNC, terminal node controller, KPC 9612 plus. This is their model TNC. Terminal node controller is the GMSK modulation and demodulation done by TNC. Actually, we know in a normal radio, that's mean transceivers, they use the basic modulation method, FM, AM, or another modulation technique. But this is the digital modulation technique, and we want to send some data, so it's a digital one. So that we have to use that type of TNC system. Okay, that TNC and radio both are connected to the PC and rotor interface. That PC install the our tracking software and ground station servers also. If you want, you can connect. Okay, this is the technical specification of the our ground station. I said you ICOM 9001. This is the some image of the our radio. This is very famous one among the amateur radio operators and some low Earth orbit satellite operation researchers. Actually, it's capable for VHF and UHF operation, also HF operation. In our case, we use VHF and UHF part because our license lie between UHF and VHF ranges also. This is another one. Next one is the TNC, terminal node controller, KPC 9612 plus 1. This is the TXC. There's a established a packet radio conversation between two nodes. Okay, actually, in 2-3, I think 2-3 decades ago, the amateur radio operators, they want to send some digital signal to one end to another end. So they use that type of TMCs. That TMCs technology, it's used the AX.25, amateur X.25. When we consider about the data communication, there are some technology and topology there. Topology mean ring, mesh, pass type of topologies there, and technology. Technology, token ring, X.25, then Ethernet. Now we use the Ethernet. Technology as Ethernet. But I think 2 decades ago, sometimes some period there, they use X.25 is the some technology for data transmission. That technology used for the radio communication in digital mode. They call AX.25. The frame called AX.25. Okay. So there's some 2 images. Upper one, there's some black thick part. This is the outdoor part. Actually, satellite tracking equipment outdoor part. The antenna directly connected to this black unit, and controller unit is the gray color one. After a few months, we used that type of 5600B ChemPro. This is the our now we used one actually. I said you 5500 also there, but 5500 system got some I think failure. After that, we replaced that 5500 in using 5600. And this is the computer interface. That means computer controller, that ChemPro controller communicate with the computer using that device. GS232B, I think you know 232, RS232 is some protocol, the serial protocol. He communicate with the computer and other devices. I think the same thing they use for this controller to communicate with the PCs. And actually, then here is the antenna type. Most right side, the image. This is the ACC antenna system. Bigger one is the VHF1 and smaller one is the UHF1. But UHF1 is the operational one for the satellite UHF band, and there's some rotor controller also, and there is software SatPC32 satellite tracking software. We use one is the SatPC32. Then this is the Psp rotor controller software. This is very special things because I think Japan and other our neighbor countries, they didn't use that software Psp rotor one, but we use. Actually, there are some good benefits for controlling the rotor because sometimes in heavy rain or heavy wind situation, antenna got some misalignment with the main boom, main boom. So in that situation, we can manage that antenna movement using that software. Actually, we can get some calibration the antenna settings through this software. So it's very good one. And then CW skimmer. This is the CW decoding software. I think you know about the CW, continuous wave. Continuous wave means just like it's like this. We know the carrier signal in radio communication. You all, I think, doing communication things. So carrier signal, in simply we call on of the carrier signal. There's no any modulation technique, just on of the carrier signal in some specific parameters. That means there's called a dit, da. It's a dit mean we call dot, and da mean we call dash, and that dot there's some specific time period, and dash there's some specific time period. Dot to dash or dot to dot there's some another specific time period. So there's some procedure. Then we can communicate with another person or another thing using that Morse code. It's a very reliable thing. Just only sound there, beeping sound there. Normally in amateur radio operators, they normally decode that in their ears, just listening and decoding. But we can do this. But in research situation, we have to document all the things, document or recording all that things. So that we have to use that type of CW skimmer software. In I think you can see there are some 𝑗𝑔6𝒦𝒄 words. This is some decoding our received signal. And another one, 𝑗𝑔6𝒦LG birds 3 RSSL. This is actually this is a real decoding when we receive the satellite. Okay. Another thing, the ground station controlling software. This software totally developed by the birds 3 project team in Kyushu University. I think Tarindu know about the more information about this software. This software I'll explain briefly. We can connect TNC and radio all together, and this software manage TNC, radio, and also SatPC32. SatPC32 is the tracking software. SatPC32 gives us to position of the satellite and Doppler correction also. Then this software integrate the SatPC32, TNC, and radio all together and operate. And we can send some command through this software. Actually, if you don't have this software, you can't communicate with the satellite. This is the some main part of this satellite communication system, especially birds 3 satellite. And this is a very small software also, and very vital one. We can decode the CW code. In CW code, it transmits every 90 seconds. Every 90 seconds, there's a 2 CW types, CW type 1 and CW type 2. CW type 1 include the battery voltages and battery current and battery temperature, and some solar cells directions. That means there are some sun direction, or there are some shadow area, or that's thing. And CW type 2, there are some gyro parameters, gyroscope parameters, and battery heater, and other special parameters there. High sampling data and cam data also, and attitude determination control systems state, and LoRa mission state. This is satellite tracking software developed by the ACCINT trainee students. Actually, I think they use Java, and this is some copy of the SatPC32. SatPC32, it's operational one. This is some research part for the in our ACCINT, and this is our final achievement. Actually, our ground station, we establishing this ground station in stretch level. So every part, everything other than the radio and PCs developed by ourselves, everything actually. In painting also done by ourselves. This is the inside of the ground station and outside antenna system. And this is our, you all know, I think these satellites, 3 satellites, one, 𝑛, and 𝑤𝑒'𝑟𝑒. We communicated with this satellite, but now they all are vanished. Okay, what we did in the ground station. This is the another thing, receiving CW, continuous wave. I told you what's the meaning of the CW and how to operate it. Morse code in every 90 seconds, transmit the CW type 1 and type 2, and we can get and decode that CDM, that CW signal. And another thing, downloading the sensor data and mission data. What are the missions? There's 3 missions, mainly 3 missions. Camera mission. There's some small camera, 5 megapixel camera. We can operate from the ground station, this camera, and LoRa mission. Actually, today our another guest, 𝑤𝑒'𝑟𝑒, he is the responsible person for the LoRa mission. He is the developer for the LoRa mission. That LoRa mission, in another part in our satellite, how to, what are the conditions to when we communicate with the satellite using LoRa. So that properties check by using this mission. I think Thandu, it's explained later. And magnetometer data missions. That means we use ADCS. ADCS means attitude determination and control system. That means satellite orientation and satellite tumbling controlled by using this ADCS. And same time we use the magnetometer for that purposes, because that turning part done by in earth magnet. We know we have a good magnetic field around the earth. That magnetic field field in the 400 kilometers, it's microtesla. It's vary in microtesla 18 to 55. In that range, vary in the around the 400 kilometers. So that magnetometer data mission, we check that magnetic field strength around the world. Then satellite health observation, battery voltages and current, battery temperature and board temperature. Actually, CW data, we can get that one. Also, we can get send some command to the satellite, and we can get all the data from the satellite. And finally, data processing and analyzing, it's done by in ground station or in 𝑤𝑒'𝑟𝑒 University, and we also submit our all receiving data to 𝑤𝑒'𝑟𝑒 University, and after that we analyzing that data. Then this is the our achievement actually. This very good historical moment, and first receiving beacon receiving received beacon time, and there's some I think other than Japan, there's 11 countries, 11 or 12 countries in our group, but we are the first transmission successful country. That means other countries they didn't do that work, but we did that perfectly, and we communicate with the satellite, and we got some images and data. This is the very good image. You can see the south part of the India, and Jaffna Peninsula also, and Pork Strait. This is very good image. It's taken by in our ground station from the Ravana 1 satellite. This commands in from the ACCMT ground station, and this is another two images. Southern part of the Sri Lanka, most left side image, and right side image. There's some landscaping image in the Sri Lanka. Land side image, and this is the some images taken from the another satellite. I think Nepali, one of the Nepali, and another one is the 𝑤𝑒'𝑟𝑒 images. They are very beautiful images also. And this is our network. Actually, 𝑤𝑒'𝑟𝑒 3 now I think expand this network. Now added another 2 or 3 countries to this network. This is our network. I think 11 operational stations and 15 members total there. And thank you very much to listen this presentation. If you have any question now, you can ask, and Taridu also joining here. Okay, thank you.
Thank you for your wonderful coverage, sir. Thanks, SatelliteandITDivision. Would you like to brief about something more about the downlink and uplink the satellites as well? Briefly.
Hello. pardon, because your voice, I think, not clear. Something, please ask again. I can't hear you clearly.
First of all, I would like to give a big thanks for your wonderful talk, sir.
Thank you.
So
Thank you.
would you like to brief about the uplink and downlink something more precisely, sir?
Sorry, you want to rate of data rate? Oh,
The context of uplink and downlink.
Dude, your voice is not clear. If you can send your question to the chat box, that would be great.
Okay, just then.
Your voice is not clear, dude.
okay. Have you any questions? Tarindu? Tarindu?
Okay. I'll
Okay.
answer for that question.
Okay.
So, Paul, can you hear me properly?
Yeah. Your voice is clear.
So, I think continuous, actually in our satellite we use that amateur radio frequency band. We use GMSK modulation, and the data rate was 4,800 bps. We use X25, I think I said that X25 packet format. So for the uplink, we use the amateur radio ground station setup. I think you saw about that one, that IC 9100 radio and those things. So basically, that's what we did in uplink and downlink. Uplink and downlink was the similar frequencies, and the both side data rate, everything is similar. But the ground station we use about 50 watt for the uplink, and from the satellite we use about 500 milliwatt for the transmission from the satellite. So that's actually what we use. And another thing, we use dipole antenna at the satellite. It had about, I think, a 1.15 dB gain. Basically, we could communicate with the satellite properly. We were able to send uplink even at, I think, maybe it was 100 degree elevation. Also, we could send a uplink to the satellite. And downlink was okay. Normally, if you get a small satellite, the biggest problem is sending uplink to the satellite. But we were successful in that case. Actually, it had a very good uplink capability. We could communicate with the satellite anytime. Anytime means if the satellite is just above the horizon, we can communicate with that one. I hope I answered that the question for the question. If you have any question, you can ask.
I was just asking about the frequency variation between the uplink and downlink as well. Why it is so? Would you like to brief something about the same, please, if possible?
Yeah, the frequency,
Yeah.
different frequencies. So actually, it is actually in Japan in QTech. We from the beginning they use a 435.313 for the uplink and 437.375 for the downlink. Actually, that was the initially they asked for the license. That is the frequency assigned by their government. So actually, there's no big reason to use different frequencies. That is what we got, and that is what we were using. So I hope that is answered.
Okay, okay, thank you.
So I can add to that one. Normally, it's better if you can have two different frequencies for uplink and downlink. Otherwise, you have to time it properly when you send with what time you are sending or what time you are receiving. You cannot do at the same time if you use one frequency for the uplink and downlink.
Thank you, Tarik sir. And I need to give you a quick announcement because there's a Q&A session at the end of this webinar. So you can submit your questions. Okay. Thank you very much, Kavindra sir. We learned a lot from your engaging presentation, and I'm confident that information will be useful for our future ground station satellite projects as well. So
Okay.
Now I would like to invite Mr. Tharindu Dayaratne to share his epic knowledge with us, and also we would like to hear more about the software.
So engineer Kavindra Sampath presented all slides. I think it's better if we go to that slide software page. Then I'll explain. So this one, actually, if you make a satellite, there are no satellite you can buy. There are some system, but if you make a satellite, that is the original one. So there are no available softwares from the internet or somewhere else. So you have to build the software for your satellite. So this is what we built for our satellite. We use Visual Studio, I think 2017 maybe. I exactly don't remember that one. For the recently I used 2018 or 19 to edit this one. So anyone can build this one. It's just simple. You have to use C#, the language. Actually, very simple software. So what we do here is we this software generate the commands, and those are basically it do two things. Generate commands and receive data. So we generate command to control the satellite. When we send those commands to satellite, we get the data. Then this software actually decode and process those kind of things will be done by this software. There are more tabs in the software. Maybe you can see. So if you go to those, actually this presentation cannot go that one. If you look at the second slide, tab is system and telemetry. If you go to desktop tab, it shows the actually do the downloaded data processing, those packet adding, missing packet showing, those kind of stuff. And what we do initially, there was no software. We start from the very beginning. So with the time we develop this one. You don't need to worry about this software development, because you start from the small step, then you later you can develop easily. So this is not much hard work. So you can do this one if you start from the beginning, and if you learn from by yourself. Okay, anything else? If you have any question, I think it's better we can start Q&A section. I think we can start the Q&A section.
So can you explain about the modulation methods and which is the most common modulation method and what is the best one?
If you go to the satellite communication, if we there are modulation which is used, but most common and best one is this GMSK, that is called as Gaussian minimum shift keying. This is the best modulation method, and there is another method modulation called, I think you saw there's a modulation called LoRa. It cannot be used for the satellite communication, for the main uplink and downlink, because there's some regulation and those stuff. But this is the common one. We have common and best one. That is why we use GMSK. And another reason also, because we use amateur radio frequencies, we cannot use different modulation, because amateur radio people say if we use a modulation, they should be able to decode that data from the satellite. That is why they actually, this is the reason they say we also should be able to decode your data, because you use our frequency band. So commonly they use this GMSK. That is why we also had to use this GMSK modulation.
Thank you, sir.
Okay, thank you very much, sir. And there's also a Q&A session. Let us now proceed to the Q&A session. I would like to ask the audience to please click on the link sent to the chat box and type in any queries you may have. If someone else has already posted the question that you wanted to ask, make sure to vote on it. Guys, that means the link for the Q&A session has been posted. You can log into that and submit your questions. If you have the same question which has been posted, you can vote to it. So you don't have to repeat the same question again. I would like to give 5 minutes to submit your questions. If you can't speak, so you can submit your questions to the Q&A link.
Vikas, are you audible?
Yes, Buddha.
The link will be sent in a minute. Okay, now you can log into that link and submit your questions. Okay, guys, the link has been posted. Okay.
They're asking about, is there a book or something about satellite complete information which you can recommend? I think there are some books. Maybe later I'll send those books to this organizers. Then they will share those things. Actually, I cannot. I quickly said the names right now. I don't remember. There are some books. Actually, one more thing. Books do not give every details. You have to find details from other satellite projects and some uh, from some people actually. Okay. This question is actually not so easy to answer. It's not actually. It depends actually. Does satellite needs a big data storage capacity? Actually, no. We use about main memory was about. We had three flash memories. Uh, One is for the camera mission and shared flash memory and the main flash memory. Each had 128 megabyte capacity. You don't need too much because let's say you use a 10 GB, 12 GB or some kind of very big uh, memory. How do you download those things? You cannot download those data using 4800 VPS. It like you can go with a very small uh, memories, but you cannot use. I think you should not use SD cards because SD card can get damaged because of those radiation in the space. If the memory get damaged, your satellite will be useless. So you have to use a better specific space tested flash memories. Okay, next question. Okay, we use NAND flash memory. So that's I think you know about my company called Micron. Actually, then they make hard disks also. There is a series called M. Actually, I don't remember exactly that one. Yeah, if you go to their website and you can find NAND flash memory. So it's a kind of like a IC. It has about 20 pins, those stuff. But it's a memory you can find from their website actually. One more thing. When you select a flash memory, you must check that one whether it is used in space in previous satellite project. Otherwise, if you select a new one, maybe let's say you use that one. If you send that flash memory in your satellite, maybe that is the first time someone sending that part to space. Maybe it will not work in the space. So because of that, you have to find the space heritage uh, flash memory from their site. Average budget for a nano satellite or a kid satellite. Wait, I need to calculate that one. I think 1 million, maybe not 1 million. 0.5 million yen, not yen, USD for $0.5 million for a one UPF satellite with building, those testing, and launching costs. I don't, there's a question, did you use ready-made solar panel or panel to round one node? Where is the question? Did you use ready-made solar panel to round one node? Your team made this. No, we cannot make solar panel. So we use very special solar panels for the space grade solar panels. We cannot make those things because those are so high technological solar panel. Even simple solar panels you cannot make. So we bought from a company. What happened in the raining? Raining, is there any signal loss? Yeah, I think you can maybe when the cloud cover comes, maybe even 10 to 10-15 dB signal loss can happen. But normally you should not operate in the rain. The ground station antenna is at very high location. You can get lightning. If lightning gets to your ground station, everything will be quiet. So you should not operate. But we know if there is rain, it's about 10 or 15 dB loss can happen. So I cannot see the question right now. Can you show me the question? Please reply one of organizer. What happened? I don't see any question.
Yes, we didn't see any question. So okay, there's any questions?
Okay, we will wait 5 more minutes for more questions.
I think question that is screen went away. So now it's not, nothing is shared right now. I think.
Rehan, are you audible? Rehan?
Okay. Yes. Guys, do you have any questions? So you can post it on the chat box. The link has been posted. Guys, there's a slight connection lost. Children, please continue posting your questions.
Okay, I think I can answer this now again. What happened in the rain? How do you guys take photos? Take a photo. So basically, when the satellite is going around us, we send a command to take a photo. That's simple. So in a satellite receive the command, it executes the camera mission, and it maybe it's about I think 10-second processing time in the satellite. Then it is done. So it's simple. And can you mention names of the solar panel company? Yeah. That is, I really don't remember that one. It's a Japanese company. It's in my, it's a Japanese name. That's why I don't remember exactly. So it is in my, maybe I can share those things. But those things are very expensive. We use about maybe about 10 panels in the satellite. One panel is about 3-inch, 1.5-inch wide, and one panel was about $300. So you have to use significant amount of money for the solar panels too. So when you buy solar panels, you cannot just buy 10 or a small amount. You have to buy 50 or something like that. The reason is when you assemble something, the reason is they don't give a small amount, and another reason is when you assemble sometimes you break also. That is very thin panels. You have to be very careful when you assemble those things. Data. What is the average power consumption of a satellite with a camera and magnetometer? When the camera mission is running, satellite consume about 1.2 ampere. This is for the Ravana 1 case, okay? 1.2 ampere in 4 volt. Okay, and normally when the camera is not running, when the satellite is just in in the nominal mode, it consumes about 300 milliamperes. That's it. So, there is there is any software for satellite design like open rocket. I think we did not use anything. We just start on the basics. If you want to learn how to do design, you have to start from a beginning, not use any kind of software or something else. What is the okay? Yeah, any software for satellite is okay. Does a cube satellite needs a big no? Yes, any question? There is any? I think I answered this question. So, is there any other new questions?
Okay. Thank you very much, Tarun sir, for clearing out all the doubts we had. Okay.
Is it question QA session finished now?
Excuse me, sir?
Q&A session finished now?
Yes, sir. It's over.
So, can I ask some question from you guys? You need to know about your so I saw you saw there's a satellite something I don't remember the name. Can you go to that slide? We'll ask simple question like how many members, what is the launching space agency, that kind of stuff. And there's a slide saying the satellite name.
Oh, your voice is not clear.
Can you hear me properly? Can you hear
Okay,
me
sir.
now? Okay. What is this satellite? Who makes this one? Your one.
Excuse me, sir. Tarundaran.
Yes, yes,
Sir, can you ask again this question?
So I saw there's a satellite you are going to make. So can you tell me about the small background of that? Can you hear me properly? If you cannot share the details now, maybe you can later and tell us. Maybe we can help you.
So, excuse me, sir. Sir, Tarundaran, sir.
Yes, we can hear you.
Sir, your audio version not proper.
Can you hear now? Can you hear?
Yes, sir.
Okay. Okay.
So can we continue this session now?
Okay, you continue. It's okay.
Okay.
Maybe we can talk later
Yes.
about the topic.
Prashant, are you debate?
Okay, thank you, sir. Now we kindly invite our participant to fill the feedback form given in the chat box. Now, I now invite 𝑤𝑒'𝑟𝑒 Karunaratne, the manager of SEDS SLTC Satellite and IT Division, to deliver the vote of thanks. Malisha?
Thank you, Prashant. Yes, I will. Thank you. Are you audible? My connection is lost now. Yeah.
Yes, Malisha, we can hear you.
Yeah. Good evening, Mr. Tarundaratne, Mr. Kavindra Sampath, and my dear friends. First and formally, I would like to thank our SatNet 2020 guest speakers, Mr. Kavindra Sampath and Mr. Tarundaratne, for attending this event, our invitation. I would also like to extend my sincere gratitude to the executive committee of SEDS SLTC for your guardians and helping hand in making SatNet 2020 a success. Finally, I would like to convey my profound gratitude and admiration to all members of SEDS SLTC, Satellite and IT Division for their invaluable assistance in making today's event a success. This event would not have been a success if it hadn't been for you. Thank you. Ashin? Ashan, are you audible? Ashan. Rehan, are you audible?
Yes, Buddhika, we can hear you.
Yes, yeah, continue.
Thank you very much, Buddhika. Our webinar has now finally come to an end. Thank you all for your enthusiastic participation and support. And I'd like to thank Sir Kavindra Sampath and Sir Tarinder Aratna on behalf of SEDS SLTC once more. So we are sorry about our inconvenience and stay home, stay safe. Thank you.